Welcome to the course on Python for data analytics, machine learning and generative AI.
Welcome to the session on logistic regression. In this session, we will explore how logistic regression helps us solve classification problems, situation where the outcome is categorical, such as yes or no, success or failure, approved or rejected. By the end of the session, we will understand not just how logistic regression works, but how to apply it confidently. You might wonder, why can't we use linear regression for classification? The key reason is that linear regression predicts continuous values, which cannot go below 0 or above 1. However, probabilities must lie between 0 and 1. Logistic regression solves this limitation by transforming outputs into probabilities. In classification problems, we are interested in estimating probabilities. Logistic regression predicts the probability that a given input belongs to a particular class. If the probability is greater than a chosen threshold, such as 0.5, we classify it into one category, otherwise into another. At the heart of logistic regression lies the sigmoid function. This S-shaped curve transforms any real value number into a value between 0 and 1. This ensures that our predictions are valid probabilities. The logistic regression model applies the sigmoid function to a linear combination of input variables. In simple terms, we first compute a weighted sum of inputs and then pass it through the sigmoid function to obtain a probability. To deeply understand logistic regression, we must introduce the concepts of odds and log odds. Odds represents the ratio of probability of success to failure. Logistic regression models the logarithm of these odds, known as the logit, as a linear function of the predictors. Unlike linear regression, which uses the least squares method, logistic regression uses maximum likelihood estimation. This method finds the parameter values that maximizes the likelihood of observing the given data. One of the strengths of logistic regression is interpretability. The coefficients indicate how a 1 unit increase in a predictor affects the log odds of the outcome. By exponentiating the coefficients, we obtain odds ratio, which are easier to interpret. To evaluate logistic regression, we use metrics such as accuracy, precision, recall, F1 score, and ROC-AUC. These metrics help us understand how well the model distinguishes between classes, especially in imbalanced datasets. The confusion matrix provides a detailed breakdown of predictions: true positives, true negatives, false positives, and false negatives. It gives us deeper insight into model performance beyond simple accuracy. Logistic regression assumes independence of observations, absence of multicollinearity, and a linear relationship between predictors and log odds. Understanding these assumptions ensure reliable model performance. To make logistic regression more robust, we can apply regularization techniques such as L1 and L2 regularization. These techniques prevent overfitting and improve generalization by penalizing large coefficients. Logistic regression is widely used in credit risk modeling, medical diagnostic, fraud detection, marketing response prediction, and many other domains where binary outcomes are involved. Logistic regression is simple, interpretable, and computationally efficient. However, it may struggle with highly complex nonlinear relationships unless feature engineering is applied.
So, let's open Jupyter Notebook
And start experimenting logistic regression in practice. Now, we will begin by importing the required libraries for implementing logistic regression and performing diagnostic checks. First, we import pandas, which is essential for handling structured data sets. It allows us to manipulate data frames, manage missing values, and prepare variables for modeling. Most pre-processing steps in logistic regression rely heavily on pandas. Next, we import NumPy. The logistic regression is fundamentally built on matrix algebra and numerical optimization. NumPy enables mathematical computation such as logarithmic transformations, exponentiation for odds ratio, and array operations. We then import Seaborn, which is primarily used for statistical visualization. It helps in exploring distributions, visualizing relationships, and generating correlation heat maps, which is also useful for checking assumptions like multicollinearity. Matplotlib is also imported for plotting. This library allows us to create residual plots, scatter plots, and other diagnostic visuals that support assumption verifications. Following this, we import stats models. Unlike purely predictive libraries, stat models provides detailed statistical inference. It gives access to p-value, confidence intervals, likelihood statistics, and formal logistic regression models such as binary, multinomial, and ordinal logistic regression. We also import train_test_split from scikit-learn. This function allows us to divide the dataset into training and testing subsets, which ensures that our model performance is evaluated on unseen data. Next, we import logistic regression from scikit-learn. This implementation is optimized for predictive modeling and supports both binary and multinomial logistic regression. Standard scalar is included to standardize features. Scaling improves numerical stability and helps optimization algorithms which converge more efficiently. To evaluate classification performance, we import classification report, which provides accuracy, precision, recall, and F1 score. We load and prepare the dataset for logistic regression analysis. We begin by loading the Titanic dataset using Seaborn's built-in function. The dataset contains passenger level information including survival status, age, fare, class, and gender. Next, we select only the variables relevant for our model. The variable survived serves as the dependent variable, while age, fare, passenger, class, and sex are chosen as predictors. After selecting these columns, we remove any rows containing missing values. Logistic regression requires complete data, so handling missing observation is essential before model fitting. We then convert the categorical variable sex into numerical form. Since logistic regression operates on numerical inputs, we map male to 0 and female to 1. This transformation allows the model to estimate the effect of gender on survival probability. Following this, we separate the dataset into independent variables and the dependent variable. The predictors are stored in X and the survival outcome is stored in Y. Finally, we add a constant term to the predictor matrix. This constant represents the intercept of the model. In logistic regression, the intercept captures the baseline log odds of survival when all predictor values are 0. At this stage, the dataset is fully prepared for logistic regression modeling. Now we will begin by checking the assumptions of binary logistic regression. First, we verify the outcome type. We print the unique values of the survival variable. Binary logistic regression requires exactly two categories. In this dataset, the values 0 and 1 represents non-survival and survival, confirming that the outcome variable is appropriate. Next, we examine the linearity of log odds assumption using the Box-Tidwell approach. Logistic regression assumes that each continuous predictor has a linear relationship with the log odds of the outcome and not with the outcome itself. To test this, we compute the natural logarithm of age, create an interaction term by multiplying age with its logarithm. If this interaction term turns out to be statistically significant, it suggests that the relationship between age and the log odds is not linear. We repeat the same process for fair. Because fair can contain 0 values, we add 1 before applying the logarithm to avoid computational errors. We then create another interaction term between fair and its logarithm. After generating this interaction variables, we construct a new predictor matrix that include both the original predictor and the Box-Tidwell interaction terms. We add a constant to include the intercept in the model. Finally, we fit a logistic regression model and examine the summary output. The p-values of the interaction term determine whether the linearity assumption holds. If these terms are not statistically significant, we conclude that the assumption is satisfied. If they are significant, corrective measures such as transformation or polynomial terms may be necessary. This completes the assessment of the first two assumptions of binary logistic regression. In this session, now we will evaluate the remaining assumptions of binary logistic regression. We begin with influential outlier using Cook's distance. After fitting the logistic regression model, we extract influence diagnostics. Cook's distance measures how much the regression coefficient would change if a particular observation were removed. We calculate a threshold using the formula 4 divided by the total number of observations. Any observation exceeding this threshold is considered potentially influential and should be examined carefully before deciding whether to retain or remove it. Next, we assess multicollinearity using the variance inflation factor. Multicollinearity occurs when predictors are highly correlated with each other, which inflates standard errors and weakens statistical inference. We compute VIF for each predictor. Values close to 1 indicate no collinearity, while values above 5 or 10 signal potential problems. We then examine independence of observation. Logistic regression assumes that each observation is independent. To assess this visually, we extract deviance residuals and plot them against observation index. If the residuals are randomly scattered around 0 without any systematic pattern, the independence assumption is likely satisfied. Finally, we evaluate sample size adequacy. Logistic regression requires a sufficient number of events per predictor variable. A common rule of thumb suggests at least 10 events per independent variable. By inspecting the frequency distribution of the survival variable, we confirm whether both outcome categories have adequate representation. Together, these diagnostic checks ensure that the logistic regression model is statistically valid and reliable for interpretation. Now we fit the final binary logistic model using scikit-learn. First, we split the dataset into training and testing sets. 70% of the data is used for training, while 30% is reserved for testing. This separation ensures that the model performance is evaluated on unseen data, which reduces the risk of overfitting. Even though 80:20 is the ideal split for train test, here we are using 70:30 to show you the difference. We remove the manually added constant column because scikit-learn automatically includes an intercept term. Next, we initialize the logistic regression model. By default, scikit-learn applies L2 regularization and uses the LBFGS optimization algorithm. Unlike stats models, this implementation focuses primarily on predictive performance rather than statistical inference. We then fit the model using the training data. During this step, the algorithm estimates coefficients that maximize the likelihood of correctly classifying survival outcomes. After training, we generate predictions on the test data. These predictions represent whether each passenger is classified as having survived or not. Finally, we print the classification report. This report provides precision, recall, F1 score, and overall accuracy. Precision tells us how reliable positive predictions are. Recall indicates how effectively the model identifies actual survivors. The F1 score balances precision and recall. Accuracy measures overall classification correctness. This completes the prediction evaluation of the binary logistic regression model. In this session, we begin implementing multinomial logistic regression using the Irish dataset. First, we import NumPy and Pandas. NumPy supports the numerical computation, while Pandas helps structural and manipulate dataset in tabular format. Next, we try importing Irish dataset from scikit-learn. The Irish dataset is a well-known benchmark in machine learning consisting of 150 flower samples across 3 distinct species. We also import the logistic regression model from scikit-learn. This implementation supports multinomial classification when multiple unordered classes are present. Additionally, stats model is imported for statistical diagnostic, particularly for checking assumptions such as multicollinearity using variance inflation factor. We then load the dataset. The dataset includes 4 predictor variables: sepal length, sepal width, petal length, and petal width. These are stored in a Pandas data frame for clarity and ease of manipulation. The target variable represents the species of each flower. There are 3 categories: setosa, versicolor, and virginica, encoded as 0, 1, and 2. Since these categories are nominal and not ordered, multinomial logistic regression is the appropriate modeling technique. Finally, we display the first few rows of both predictors and the target variable to verify that the data has been correctly loaded and structured. This prepares the dataset for multinomial logistic regression modeling. In this section, we fit a multinomial logistic regression model using the Irish dataset. We initialize the model by specifying the multi-class parameter as multinomial. This ensures that a softmax function is used instead of a one versus rest approach. The softmax formulation allows all 3 species categories to be modeled simultaneously with a single optimization framework. The solver is set to LBFGS, which is a quasi-Newton optimization method suitable for multi-class classification. Because multinomial models sometimes require more iterations to converge, we increase the maximum iterations to 200. Next, we fit the model using the entire dataset. During this process, the algorithm estimates coefficients that maximize the likelihood of correctly classifying flower species. Finally, we compute the model's accuracy using the score function. This calculates the proportion of correctly classified observations. Since the evaluation is performed on the same data used for training, the accuracy reflects the training performance rather than generalization ability. Typically, the Irish dataset yields very high accuracy because the species, especially setosa, are well separated in feature space. The dependent variable satisfaction contains 3 ordered categories. The model estimates cumulative log odds using the proportional odds framework. Each coefficient reflects the influence of a predictor on the likelihood of being in a higher satisfaction category. A positive coefficient indicates that as the predictor increases, the probability of belonging to a higher satisfaction category increases. Conversely, A negative coefficient suggests a greater likelihood to be falling with the lower category. To summarize, logistic regression is a powerful classification technique that models probabilities using the sigmoid function and maximum likelihood estimation. With proper evaluation and regularization, it becomes a robust, reliable tool for decision making.
Thank you.